Hi, welcome to the session. In this session, we'll be discussing about the shape of the magnetic circuit, the core part. So, in the last session, we had a discussion about core features, okay, the lamination process and the stacking factor and then core staggering also we have discussed. And here in the session, we will be discussing about what should be the shape of the core. We know that the core has to be designed with steel laminations or silicon steel laminations. Okay. So, here the cross sectional, the shape is nothing but here cross section of the transformer core is made up of steps instead of having square shape. So, why don't we go for square shape core and why do you go for stepped core is a question here. There are some advantages. Let me show you that. Here. I have a square shape core. Okay. So, if I have a square shape core, it will be like this. Right. Now, if core is there, what is the electric potential of the core? The voltage in the core is 0. Electric potential is 0. But it will be having magnetomotive force. Magnetic potential will be there. Electric potential is 0. Right. Now, around the core, we have to place a winding. Now, I cannot place a winding directly around the core. First, I have to place insulation. And then next I have to place a winding. Right. So, the winding may be I am representing with another color. Right. So, here the winding will be like this around the core. Alright. I am not showing both the windings. I am just showing only one winding. First part is core and then next part is insulation and the next part is winding. So, let me show you the colors also if it is possible, and this color is winding, yellow color is insulation and the white color is going to be the core. So, we are not placing the winding around the core directly. Between the core and windings there is a insulating medium. Why? Because winding is connected with the supply. It will be having some electric potential and it will carry some current. So, whenever you place directly the winding onto the core, definitely it will lead to a short circuit, it will lead to a current flow in the core also. So, to avoid a short circuit problem and to avoid the current flow, unnecessary current flow in the core, we will be placing the insulation. Right. So, the core and winding is separated by an insulating medium. The insulating material can be paper, can be paint. Generally, we will be placing the paper, impregnated paper. Impregnated paper is nothing but the normal paper dipped in a transformer oil. If the paper is placed in a transformer oil, the paper will absorb the oil. Therefore, the dielectric strength of the paper will increase. If the dielectric strength of the paper will increase, it can withstand more amount of voltage. Okay. So, let me just give me a minute. It can withstand a more amount of voltage. Alright. See, now if this is a square shape, to place the winding, of course, before the winding we are placing insulation. Here, I have an air gap between the core and winding here, and I have an air gap between core and winding here, and I have an air gap between core and winding here. Why the air gap is coming? Because of the presence of sharp edges, air gap between core and winding is existed. So, this part I am calling it as air gap. This part I am calling it, this color I am calling it as air gap. Okay. Alright. So, in order to, if air gap is more, reluctance is more. If reluctance is more, magnetization is not proper. Magnetization is not going to be proper. So, here because of more reluctance or because of air gap, the magnetization is not going to be complete. The magnetization is going to be maybe less than 100%. So, that I can call it as the utilization factor of this square shape core is going to be less than 100% or less than unity. What I can call it as less than 100% or less than unity. Okay. Now, if you look at If you look at another core, what is another core? He said step core. That means what? Stepped core are also called as cruciform core. So this is a square shaped core. This is a square shaped core, and let me show you stepped core. The stepped core will be like this, the same core only. What we do is we cut the edges. We cut the edges simply. We cut the edges. Okay, here and here and here. If we cut the edges, it will look like this. Okay, let me show you here. This is two steps. Two steps. Two steps. Two steps like this. So because of here edges are absent, as the edges are absent, you can place the insulation very near to the core. Very near to the core. If you place the insulation, you see how it will be. So this is how the insulation, and you see the air gap between the core and insulation, the air gap between the core and insulation is very minimum. And upon this I can place a winding. Upon this I can place a winding. So the winding is also very near to the core. The winding is also near to the core. So I can say that because of presence of edges, the length requirement per turn, the length requirement per one turn, like this, one turn means it's a turn, right? Like, okay, it is, you are turning it, the winding. So the length requirement per turn is going to be increases, whether it is insulation, whether it is winding, in the above case. If the shape of the core is square shape, the length requirement per turn, the insulation length requirement per turn is more, and the copper length per turn also going to be more. If copper is more, insulation is more, obviously the weight is more. If the weight is more, size is more. Obviously it will be more size. If copper is more, copper losses are more. But when it comes to here, here air gap is less. So here the air gap is very small. Here the air gap is very small. Here the air gap is also very small. So I can say that the reluctance offered by this path, is very less than the reluctance offered by this one. Okay, the reluctance offered is more, and hence I can say that no doubt the magnetization is going to be little less, and when it comes to here, the magnetization is going to be more. I can say that uniform magnetization can take place in the stepped size, in the stepped core, or otherwise cruciform core, whereas non-uniform magnetization takes place, or not complete magnetization, I can say, in the square shaped core. So let me repeat once again. Square shaped core requires more length per turn insulation. Square shaped core also requires more copper per turn requirement. And because of sharp edges, there is an air gap between the winding and core, and because of air gap, reluctance of the core is going to be increases, and hence flux establishment will be opposed. So the core cannot be completely magnetized. When it comes to stepped core, the length per turn requirement, insulation requirement, copper requirement is less, and air gap between the core and winding is also less. As air gap is less, reluctance is less. If reluctance is less, magnetization can be enhanced. So the core is going to be approximately, it's around 100% utilization factor. Around 100% utilization factor. Okay, right. Now what is other parameter I can say? When I am saying about more insulation, more winding, I can say more winding means more winding losses, no. Less winding means less winding losses, no. So stepped shape, stepped core, or otherwise we also call it as cruciform core. This is cruciform core or stepped core. Cruciform or stepped core. Okay, and this one is square shaped core. The square shaped core requires more copper and results in more copper losses, and stepped core requires less copper, results in less copper losses. And moreover, utilization factor of the magnetic path is completely magnetized. So that's the reason why we choose stepped core rather than square shaped core. Okay, so these are the advantages. I can say you can see the cruciform core reduces the diameter of the circumscribing circle. Circumscribing circle means the outer layer. Because of absence of edges, then you see the dia here. Dia will be lesser. Due to less dia, it requires less insulating material, the less amount of copper void, whatever the points we have discussed so far, that is the thing. So as less winding, less insulation and less amount of core also, because of that the size and weight is also going to be less for a cruciform core shape transformer. Okay, cruciform core also has more utilization factor, so that these are the points we had a discussion. That's the reason why cruciform core is more advantageous than the square shape. Okay. Now we will see some questions. We will see some questions on the core, on the core or magnetic path. Here the question is the desirable properties for a transformer core material is, or core materials are. What are the desirable properties? How the core should be? Core should be designed with ferromagnetic material. That is not a property, that's a material. And the ferromagnetic material will possess high permeability and low reluctance. Let us check this. He has given low permeability and low hysteresis loss, high permeability and high hysteresis loss, high permeability and low hysteresis loss, low permeability and high hysteresis loss. Loss should be always less, na? Loss should be always less, na? No, you should not design any part with high loss. It should be always, every part should be providing, should result in less loss only. So whatever the loss, wherever the loss which is given high hysteresis loss, you can cancel it. High hysteresis loss, you can eliminate it. So option B and option D can be eliminated, and option A and option C could be any one of that answer. Okay, so low hysteresis loss, and permeability should not be low, permeability should be high. High permeability, so that the flux lines can be easily established, and the orientation, the domains in the steel material will be easily magnetized or will easily change its direction according to the external magnetic field. Okay, all right. So let's move on to the next question. If you move on to the next question, it will be like this. This is a question. Here the question is, which of the following will improve the mutual coupling between primary and secondary circuits? Between the two coils, how can you enhance the coupling? You have seen, na? The transformer oil of a high breakdown voltage, high reluctance magnetic core, winding material of high sensitivity, high resistivity and low reluctance magnetic core. Okay, just by placing the magnetic path, we can enhance the mutual coupling now, because the core has to possess low reluctance. If it can possess low reluctance, then all the flux lines can be diverted onto the second coil side. So this is the only answer. All right. So let's move on to the next question. The question he has given it as laminated insulation, coated with winding. Laminated insulation, coated with varnish is a staple adoption in transformer assemblage in order to. Okay, so it's like laminations. It's like it should be laminations actually. Laminations, insulations, insulation or insulating material. It should be actually like insulating material or insulating material coated with varnish. So insulation is of varnish and the laminations are there. Laminations means small area of cross section, thin sheets. So the laminations, insulating material is a staple adoption in transformer assemblage. So if you want to design a transformer, if you want to assemble a transformer core, what we do? We take the help of thin sheets. Between each and every thin sheets, we will be placing the insulating material. The insulating material can be paper, can be paint, can be varnish. That is what. So this, we will be adopting the insulation, we will be adopting the steel laminations also. So in order to what? In order to reduce the reluctance of the magnetic path, in order to minimize the losses due to eddy currents, in order to increase the reluctance of the magnetic path, in order to increase the effect of eddy current. Why are we going for laminations? Laminations, why do we go for laminations? Laminations means here it is thin sheets, thin area of cross section, thin sheets. Okay, the area of cross section of each and every lamination is not even more than 2 mm to 5 mm. Okay, the thin sheets, the area of cross section is hardly 2 mm to 5 mm. Okay, because of smaller area of cross section, the resistance offered by the core material is going to be very high. If the resistance is very high, the eddy current is going to be reduces. If the eddy current is reduces, eddy current loss also reduces. If the resistance of the core is more for a smaller area of cross section, eddy current strength will be reduces and hence eddy current losses reduces. So why are we choosing laminations? To minimize the eddy current losses, not to minimize the reluctance. Main thing is to minimize the losses due to eddy currents. Okay, I hope it is clear, I think. So let's move on to next question. Here the question is given as, in a core type single phase transformer, the steel core is assembled by staggering butt joints in adjacent layers of laminations. He has given, shown in the figure. The purpose served is said to be. Why are we, the purpose served is said to be. He has given like avoiding continuous air gap, preventing loss of mechanical strength, reducing eddy current loss, and the question is here, question starts here. Which of the above statements are true? Which of the above statements are true? Is it only 1 and 2? Or 1 and 3, 2 and 3, 1, 2, 3. Okay. So he said that steel core assembly. So he has given some laminations and he has given some butt joints also. Why do you choose these butt joints? The main intention of butt joints at the adjacent layer is to increase the mechanical strength. In order to increase the mechanical strength. So in order to preventing the loss of mechanical strength. Preventing loss of mechanical strength, increasing the mechanical strength only. Na? So 2 is absolutely correct. Okay. If you don't create a joint, what will happen? If you don't create a joint, air gap takes place. So avoiding continuous air gap. This is also correct. And the third one, reducing the eddy current loss. Okay. Reducing the eddy current loss. Here, eddy current loss can be minimized by using laminated steel. Did he mention that in a core type single phase transformer, the steel core is assembled by staggering the butt joints in adjacent layers of laminations. The purpose is said to be, okay. So he is specifically mentioning about butt joints. So butt joints are to increase the mechanical strength to avoid the air gap. Okay. If he mentioned that laminations, then reducing the eddy current losses could be the answer. So as he is mentioning specifically about butt joints, so 1 and 2 could be the correct answer, but not 3. Do not include 3. Because reducing eddy, but by creating butt joints, you will not get reduction in eddy current. No. Addition of silicon reduces the eddy current loss. Making thin laminated sheets, you will get the eddy current loss. Of course, laminated steel only, but he is mentioning all about butt joint. So be careful about this point. Otherwise, most of the people would have gone for, will go for the other one. That is fourth option. So here, now we will discuss about type of the magnetic circuit. Before this, we have discussed about shape of the magnetic circuit. The shape must be cruciform core shape, but not square shape. And here we will discuss about type of the magnetic circuit. Okay. So we have two types generally, core type and shell type. In the last session, we have seen how a core type magnetic path looks like, our shell type magnetic path looks like. While discussing about laminations, in a core type magnetic circuit, the laminations are of L shape or 7 shape. In shell type magnetic path, the laminations are of M shape and I shape, or otherwise W shape and I shape. So shell is a That construct. Shell is a M shape and I shape. That is a shell type magnetic material. L and 7 is a core type magnetic circuit. Okay. So let me show you here core type and shell type. So I have, let me take up here core type. Let me take up here core type. If I go ahead with the core type, it looks like this. So I have a square shape. All right. So this is my core type construction. On this, I am going to place winding. If I use more number of turns, I can call it as high voltage winding, and I am calling it as N1. If I use less number of windings or less number of turns, I can call it as low voltage winding, and I am calling it as N2. Okay. So here N1 is greater than N2. So N1 is high voltage winding and N2 is low voltage winding. The number of turns are, you see, 1, 2, 3, 4, 5, 6, and here the number of turns are hardly 4 turns. So more number of turns on this side, so I am calling it as N1 as high voltage winding and N2 as low voltage winding. Don't call them as primary winding and secondary winding. Until unless you give the supply, you cannot decide the winding as primary or secondary, because you can give the supply here. If you give the supply here, it will become primary. If you give the supply here, it will become primary. Okay. Now if you see the construction of the core type construction, here I have a core. Now around the core I have winding. I have the winding. All right. So I can say that winding is surrounded by the core. Okay. Winding is here, there is a winding. I am placing the winding on the core. So winding is surrounded by the core. That's the first point I can say. It has two limbs. Two limbs are nothing but legs. The vertical portion, we can call it as limbs. Okay. Limb 1 and limb 2. Two limbs. Okay. Leg 1 or leg 2. Limb or leg, anything is okay. Limb or leg, anything is okay. Leg or limb. Limb or leg, both are same. The vertical part of portion, the vertical part of the magnetic circuit, you can call it as limb or leg, right? So the winding is surrounded by the core, and if you see here, if I am going to give you some, if I give any voltage, if I give the voltage here, and this voltage source is going to drive the current, and the current is going to set up the flux lines. Okay. Now if you see the flux lines, it will be like this. If you see the flux lines, it will be like this. So let me show you the flux lines with a different color. Okay. So the flux lines are going to be like this, So okay. So the flux lines are like this. Maybe I'm substituting the direction also. I'm indicating the direction also. So this is the mutual flux for N1 coil and N2 coil. I just took a direction in a random way. If you want to apply right hand thumb rule, you can apply right hand thumb rule. As a current is going like this in the front side and back side like this. So you can apply right hand thumb rule and you will get the flux direction upward. Okay. So this flux is produced due to this current. Okay, right. So now the produced flux is linking with N2 turns and N1 turns, N2 turns and N1 turns. That's why I am calling that flux as mutual flux. I am not representing any leakage flux here for time being. I am assuming that 100% flux is linking with the coil 1 and coil 2. No leakage flux, zero leakage flux. Okay, so if you see, I can say that whatever the flux which is produced here, the flux is common for both the coils. So I can say that flux is not getting divided between the coils, flux is same. So I can call this magnetic circuit as series magnetic circuit. I can call this magnetic circuit as series magnetic circuit since flux is not divided. Since flux is not divided or undivided. Okay, flux is not divided. Okay. Here one more point, he is saying that there is a chance of, he is saying that the leakage flux is more, hence the power transfer capability is less. Leakage flux is more means, I said that just now, I said the leakage flux, I assumed it as 0. Let us create leakage flux also. If you create flux on this side here there is a flux, here also there is a flux. If you keep some amount of load, here there will be a flux and here also there will be a flux. Okay, so this flux is linking with phi 11 is linking with N1 only, phi 11 maybe phi 22 is linking with N2 only. So more possibility of leakage flux. Okay, that's the reason why if leakage flux is more, mutual flux is less. If leakage flux is more, phi 11 if it is more, and definitely phi 12 will be less, therefore EMF will be less, and hence the power transfer capability is also going to be less. Because if mutual flux is less, definitely mutual induced EMF is less, and hence we cannot transfer large amount of power when voltage is less. Alright, the other point he is saying about both the limbs have same cross sectional area. Both the limbs has same, even not only limb, even yoke part also, horizontal portion also, limbs and legs, yoke and legs both have same cross sectional area. Fine, whatever the area which is, if the area occupied by the leg is A1, area occupied by the yoke, area occupied by this leg and this yoke, all are same area, A1 only. Okay, and the other point he wants to say about requires more copper and less insulating material. Requires more copper and less insulating material. Why? If you look at the leg, here, on this leg, I am placing only one winding, that is high voltage winding. Okay, I am placing one winding, right? So here, if this winding voltage rating is around, let us say 220 kilovolts, if I apply 220 kilovolts. Now the potential difference between winding and core is how much? 220 kV minus 0 volts. We will be getting it as 220 kV only. So the thickness of insulation required between the core and winding, maybe it is, I am writing it as T1. Similarly, the thickness of insulation required between low voltage winding and the core, if I take up it as 220 kilovolts divided by 11 kV. Now here the thickness of insulation is proportional to 11 kV minus 0. It will be T2 only. Definitely T2 is definitely less than T1, because here more potential difference, more impressed voltage I can say, because more voltage I am applying on the high voltage side, less voltage is generated on this side. So to withstand less voltage, less thickness of insulation. Okay, to withstand more voltage, more thickness of insulation. Okay, here as only one winding, only one voltage level is there, I can place only one insulating material. I can place throughout this length, I can place one thickness of insulation here and there. Okay, no other winding is there. I don't have high voltage winding and low voltage winding, If you have combination of windings like in shell type construction, then it will be difficult. That's the reason why he said insulation requirement is going to be less. So you can use completely more copper for throughout the length of the leg, you can use and completely 220 kilovolts winding. So you can place more amount of copper with less insulation. Okay, so that's why as it is more number of turns are there, less insulation is there. Because of less insulation, you can operate it at high voltage rating. Okay, less insulation means only one thickness of insulation. Please remember that one. I'll show you in the shell type construction. Okay, only one thickness of insulation. So you can go for high voltage ratings, and if it is high voltage rating, it will carry small current. So therefore, I can call it as small kVA ratings. Power rating is small, voltage rating is large. Power rating is small, voltage rating is large. Okay. So here the other point I just missed here, windings are not protected by the core, because core is going to be protected by winding. Windings looks like windings are covering the core. But if you see the another part, it looks like this. If you see the another part, it looks like this. In a shell type construction, it will be like this. The side limbs area of cross section and the yoke area of cross section is going to be same. The side limbs area of cross section and yoke area of cross section is going to be same. Okay, so this is leg 1, leg 2 and this is yoke. Okay, all these are having same area of cross section. Let me write it as A1, A1 and A1 and A1. Okay, right, but the middle one is there na, this one is A2. So here middle limb is double the side limb, A2 is double the side limb. Middle limb is of larger area of cross section compared to side limbs. Whereas in the core type construction we have seen both the legs have same area of cross section, and here middle leg has double the side legs cross section. Our side legs are half of the middle leg. Anything is okay. And now we are going to place a winding. Same, let us place 220 kilovolts by 11 kilovolts. 220 kilovolts by 11 kilovolts. If you want to place 220 kilovolts winding, here, I have to place more number of turns. But the leg is of this much length only. I cannot place the high voltage winding completely, because I have to place low voltage winding also on the same leg. Therefore, I am stopping the number of turns here. So this is my 220 kV winding, which is N1 turns. Okay, so here 220 kV winding, N1 turns. Now I just wanted to go with another winding. The another winding is, maybe let me take up it as 11 kV winding, and let me show you with another color. This is my 11 kV winding. Okay, less number of turns, N2, and which is of 11 kV winding. So what I can say here, on one leg itself you have to place both the windings. You cannot use complete leg for whole winding. As you are not able to use complete leg for whole winding, you cannot place more amount of copper. In the previous case, if you see, more amount of copper can be placed here. That's why he said requires more copper. But here you cannot place more copper throughout the leg. You can place only part of the leg will be occupied. Only part of the leg will be occupied by high voltage winding, and other part of the leg will be occupied by low voltage winding. So less copper placement is you can place only, you can put less amount of copper. And moreover, one more point is there we have discussed about more copper, less insulation. Here less copper and you need to put more insulation. Why? This side 220 kilovolts potential and this side 11 kilovolts potential. These two potentials are acting on the same leg na. So the thickness of insulation required between the core and winding, and between the 11 kV and 220 kV also. 220 kV and the core. The potential difference between high voltage winding and the core, the potential difference between low voltage winding and the core, and the potential difference between high voltage winding and low voltage winding. Three different thickness you will get. So here the insulation requirement is going to be more. That is what, less copper and more insulation. Requirement, as you are keeping different thickness of insulation. And moreover, if you are increasing the voltage, the operating voltage, it can create the stress on the other winding also. Because electric field intensity, whenever you increase the applied voltage, the electric field intensity also increases, and it will create the stress on the neighboring parts also. So if you increase the voltage on high voltage winding, it will create the stress on low voltage winding also, and it may lead to failure of thickness of insulation on the low voltage side, because it can withstand high stress lines, high stresses. That's the reason why, to withstand those stresses, we usually place more amount of insulation. So do not operate at high voltage. You should operate at less voltage. So it is economical for low voltage operation. If it is operating at low voltage, then you have to design to operate at large currents. So low voltage, large currents. Large current is nothing but large kVA. Large current is nothing but large kVA. Okay. Now the other point you see, the first point here, it has 3 legs. 1, 2, 3. 1, 2, 3. Okay. Now here, this is a core and this is a winding. Winding is in middle and the core is side. So winding is surrounded by the core, na? Winding is covered by the core, no? You see, windings are being surrounded by the core. Winding is covered by the core. So it has a protection. In the previous case, core is surrounded by the winding. Winding doesn't have a protection. Here winding has a protection. And you see, if I give a supply, the supply will drive a current and that current will produce a flux lines. This flux lines, let me show you, this flux lines will divide into this side and also divides into this side equally. Why? The middle leg has double the area of cross section and the side legs has same cross section, that is A1 only. As the area of cross section is same, reluctance offered is same. If reluctance offered is same, flux division will be done equally. If the flux in the middle part is phi m and the side part will be phi m by 2. It also will be phi m by 2. Okay, this is also will be phi m by 2. So as the flux is getting divided, you can call it as parallel magnet path. In the previous case, flux is not getting divided. In this case, flux is getting divided. That's the reason why you can call it as parallel magnetic circuit. Okay, windings are well protected by the core. Windings are being surrounded by the core. It has 3 legs. We have discussed this. The other point is leakage flux is less. How can you say that leakage flux is less? You see, if the flux produced by the 220 kilovolts is there, most of the flux is choosing the low reluctance path. If any amount of flux is establishing like this, if any amount of flux is establishing like this, you cannot call it as leakage flux. Okay, though it is phi 11, though this is phi 12, okay, right, though this is phi 12, you cannot call the phi 11 as leakage flux because phi 11 is a part of the phi 1 and that is produced due to high voltage winding. The high voltage winding flux line is linking with the low voltage winding also, no. Phi 11 here linking with high voltage winding is creating the phi 1. High voltage winding is creating the phi 1. Okay, alright. So right, now this phi 1 is divided into phi 11 and phi 12. This is mutual. Okay, and phi 11 is also linking with high voltage winding and low voltage winding. If phi 11 links with only high voltage winding, we would have called it as leakage flux. But phi 11 is also linking with other coil. Phi 11 is producing due to high voltage winding and also linking with low voltage winding at the bottom, no. So you cannot call this as it is not leakage flux. Not leakage flux. Why? Because this phi 11 is linking with N2 and creating an induced EMF, mutual induced EMF. Whatever the flux which doesn't participate in the production of mutual induced EMF, that is a leakage flux. Okay, whatever the flux which doesn't participate in the production of mutual induced EMF, that is a leakage flux. But here phi 11 is linking with the N2. That's the reason why leakage flux is minimized. So leakage flux lines are here less, and hence if leakage flux line is less, no doubt EMF is going to be more. If EMF is going to be more, power transfer capability is going to be more. Okay, so we have seen already the area of cross section of the outer legs will be half of the middle link, right? We have seen, right? You see here, if you want, in this case, this is leakage flux. The leakage flux is linking with only N1 turns, not linking with N2 turns. Okay, all right. So that's the reason why leakage flux creates or plays a major role in delivering the power to the load. Okay, be careful with the leakage flux lines component. All right. So now by looking at the previous types of magnetic circuits, we came to know that core type construction has more leakage flux lines. Okay, shell type construction or shell type magnetic path has less leakage flux lines. Okay, so power transfer capability is more for shell type and power transfer capability is less for a core type. Alright. Now the question is, how can you minimize the leakage flux lines? If you can minimize the leakage flux lines, power transfer capability can be enhanced. How can you minimize the leakage flux lines? The winding should be, you should not place only one winding on the leg. You should place high voltage winding, low voltage winding, high voltage winding and low voltage winding. Even on the core construction also, core type magnetic path also, you have to place half HV, half LV, half HV, half LV. Therefore, if any flux is establishing through air gap, that will link with the low voltage winding. If any flux is established with the through the air gap, that will link with the low voltage winding or high voltage winding. So, no chance of having leakage flux lines. Leakage flux lines can be minimized by designing interleaved winding. Interleaved means half here, half HV here, half HV here, half LV here, half LV here. First leg, second leg. Okay, half HV here, half HV here, half LV here, half LV here. Interleaved winding will help us to minimize the leakage flux lines. The main purpose of interleaved winding is to minimize the leakage flux lines. You see here, I have a core type construction and this is completely maybe a high voltage winding and this will be completely a low voltage winding. So definitely you get leakage flux lines here. Okay, so here there is a leakage factor can be defined in another way. Height of the window, H is nothing but height of the window, W is nothing but width of the window. Okay, so here height of the window, let me write with another sketch. Height of the window divided by width of the window. Okay, if window width is more, I can say that window width is more, leakage flux is more. I can call it as, if window width is more, then leakage flux is more. Leakage flux is more. We call this as window factor actually. We call this as window factor. Okay, if width of the window is more, window factor is less. If window factor is less, leakage flux is more. Leakage flux is more. Okay. So here, so far we had a discussion about the types of magnetic circuits and the shape of the magnetic circuit, leakage flux component and all those things. Let us move on to the other part. What is the other part? Apart from magnetic path, the other part is windings. Okay. So the windings, how do you place the windings? Here winding can be of copper material or otherwise aluminum material. Generally we choose copper material. Rather than aluminum material. Okay, right. We choose copper rather than aluminum because copper has more mechanical strength than the aluminum. This is a very important point. Copper has more mechanical strength than aluminum. Okay, if you turn the aluminum for 1 or 2 turns, then it will break down. The mechanical strength of the aluminum is very less now. That's the reason why we don't use. Though the copper has a little more resistance, we prefer copper only. The only reason is copper has good mechanical strength and that's the reason why. And moreover, you can go for laminations, many strands. But aluminum, if you are going for strands, the mechanical strength still decreases. Aluminum has less mechanical strength, and if you are going for strands, still the mechanical strength is going to be very less. Okay, so that's the reason why copper is the best option for us for the winding material. Okay, now how to place a winding on the cores? You see in the previous diagram, you see in the present diagram. The previous diagram we have got here, you can take up, let us take up only high voltage winding, HV only, and here LV only. In this LV and HV, you see LV and HV. Okay, LV is near. This is one is LV and 2 is HV. Okay, that means what? Half LV here, half LV here, half HV here and half HV here. We call this winding as interleaved winding. So what is the main intention? Behind the interleaved winding? The main intention behind the interleaved winding is whenever a flux produces by the low voltage winding or high voltage winding, it can link with the high voltage winding and low voltage winding. So leakage flux can be minimized. Leakage flux can be minimized. Okay, if the leakage flux is minimized, power transfer capability can be enhanced. Mutual flux is going to be increases, EMF increases, and power transfer capability will be increases. Okay, so this keeping half HV on one side, half HV on the other side, keeping half LV on one side, keeping another half LV on other side is called as interleaved winding. The interleaved winding main purpose is to minimize the leakage flux lines. Remember this point, this is very, very, very important. Okay, you can see that's a square type construction, right? That's a core type construction, by the way. Now what about the shell type construction? You see, this is a shell type construction. This is a middle limb. This is A2. All right, this is A2. So I have A2. So this is A2 and this is A1. Of course, this is also side limbs. Yokes also A1 and this is A1. So we know A2 is double the A1, side limbs area of cross section. You see, this is height and width is this much. So width of the window, height of the window. Width of the window is less. If width of the window is less, window factor is more. If window factor is more, I can say that leakage flux is less. If window factor is more means leakage flux is less. Okay, remember this point. If window factor is less, leakage flux is going to be more. Yes or no? Here, whatever the flux which is established through the air gap, it will link with the high voltage winding and low voltage winding, high voltage winding and low voltage winding. And you see here, high voltage winding, this hashed portion is called as insulation. Okay, and the remaining, the white portion is called as winding. So it can be high voltage winding, insulation, low voltage winding, insulation, high voltage winding, insulation, low voltage winding, insulation. It's like bread, butter, bread, butter, bread, butter, and so on. It's like sandwich. Okay, this winding is of sandwiched winding. Whether it is interleaved winding or sandwiched winding, both will minimize the leakage flux lines. Okay, so we call this winding as sandwiched winding, sandwiched nature winding. Okay, sandwich nature winding is also mainly to minimize the flux line. So it will also decreases the flux line, leakage flux line. So that power transfer capability will be enhanced. Okay, so let us move on to the what I can say, the placement of winding. If you see, I have a middle limb like this. Okay, so this is a top and bottom of the core. This is top of the core and the bottom of the core. Now here I want to place a winding now. To place a winding, first of all I should place a insulation. So let me take up insulation here. So this is the insulation thickness. Okay. Next I have to place a winding. I am placing the low voltage winding. Let us assume low voltage winding. This is LV. Okay. Now after LV you need to place insulation and then HV. LV, HV, of course in between insulation. If I ended with high voltage winding, then the thickness of insulation requirement, here it is going to be T1 and here it is going to be T2. Why? Because high voltage winding voltage rating is more. Now the potential difference, if I assume it as going to be 220 kilovolts and then here core is of 0 volts, the potential difference is going to be 220 kilovolts. To withstand 220 kilovolts, the thickness of insulation is going to be T2. Let me assume it as 10 mm. Let me assume it as 10 mm. Okay, let me assume it as 10 mm. Okay, T1, let me assume it as just 2 mm. Okay, because LV voltage rating I have assumed it as 11 kilovolts and core is of 0 volts. So 11 kV minus 0, the potential difference is 11 kV only. To withstand 11 kilovolts, I require just 2 mm. I am assuming that. To withstand 220 kilovolts, I require 10 mm. Okay, now see, the distribution of insulation at the top and bottom is not same. Okay, now the distribution of insulation at the top and bottom is not same. In order to have symmetrical distribution, we don't prefer we don't prefer this kind of arrangement. What we prefer? We prefer half LV at the top, half LV at the bottom. Therefore, if it is half of the LV, therefore the thickness of insulation required here and the thickness of insulation required here will be same now. So here also T1 and here also T1. Here also T1. Because at the top of the core, near to the top of the core, the thickness is going to be T1. At the bottom of the core also T1. Because at the top low voltage winding is there, the bottom also low voltage winding is there. Why don't you keep high voltage winding at the top and bottom? If you keep high voltage winding at the top and bottom, we require more amount of thickness insulation. In between low voltage winding and high voltage winding, if you see the potential difference, 220 kV minus 11 kV. So if I remove 10 kV, then it will be 210 kV or 209 kV. That means what? To withstand 11 kV, I got 2 mm. To withstand 220 kV, I got 10 mm. Now to withstand less than 220 kV or 210 kV, it might require 8 mm or 7 mm. That means what? The insulation between HV and LV, this is going to be T3. If I take up it as T1 as 2 mm, T3 as 8 mm, and the insulation between HV and HV and core is 10 mm. I did not place high voltage winding near to the core. You see here, near to the core I did not place. Here also I did not place. I placed high voltage winding in between. Therefore, the total thickness, how much you are getting? 8 to, it's a 10 mm combination only. 2 to 8, 8 and 8 and 8 and 8 and 8 and 2. But if you place high voltage winding near to the core, you would have get 10 na. So the thickness of insulation requirement is going to be, the thickness of insulation requirement would have been increase. Okay. So that's the reason why we don't place high voltage winding near to the core. If you place high voltage winding near to the core, the thickness of insulation is going to be increases. Placing low voltage winding near to the core is an advantageous, that it results in less amount of thickness of insulation. Okay, all right. So there is one more point also. If you place low voltage winding near to the core, there is one more advantage also. Let me tell you about that one. If I take up any transformer, maybe a core type construction or a shell type construction, please try to understand here. I am placing a insulation first. Okay. So this is the core. Near to the core, I have to place low voltage winding. So before placing low voltage winding, I am placing insulation. Okay. This is my red color is insulation. Now I am going to place a low voltage winding. This is LV. This is LV. And then half here, half here. That means what? After the LV, I have to place again insulation. This insulation has to withstand high voltage winding, potential difference between high voltage winding and low voltage winding. So now I am going to place the high voltage winding here. So this is HV and this is also HV. This is a turn aside and this is a side. Complete turn will be having two sides, na? This side and this side. So this is a side, one side of HV and this is another side of HV. This is one side of LV, there is another side of LV. Okay, right. So what I am trying to say is, because of placing low voltage winding near to the core, the thickness of insulation is how much here? The thickness of insulation is how much here? Maybe 2 mm and then 8 mm. So altogether it will be 10 mm. Okay. If I place high voltage winding near to the core, it will take first thickness will be 10 mm and next thickness will be potential difference between high voltage and low voltage winding. It requires 8 mm. So 10 plus 8, 18 mm it will require. Did you understand? If I let me show you on this side. Okay. If I place high voltage winding near to the core, I have to place here first 10 mm thickness and then high voltage winding. Okay, this is my HV part, and then I have to place insulation. Okay, then I have to place the low voltage winding. Okay, LV part. LV part. If you see the thickness of insulation between HV and core is 10 mm. Potential difference is 220 kV minus 10 na. I just assumed, I am just going with a random number. Come with the previous continuation only. The potential difference between HV and LV is 220 minus 11 kV. It's 209. So it will be taking 8 mm. So totally how much it will be? 18 mm we require. Here only 10 mm. If you go with this kind of arrangement 10 mm, if you go with this kind of arrangement 18 mm. So we choose LV winding near to the core. So this one is definitely less than this one. So let me take up it as TL and okay, let me take up it as T1 and T2. T2 is second method of arrangement, T1 is first method of arrangement. 1 is first method of arrangement, 2 is second method of arrangement. So T1 is less than T2. Okay, so I can say that therefore we prefer LV near to the core. LV near to the core. This is the advantage. Okay. Now, what is the additional advantage? You know, the additional advantage is here we are going to place the tappings. We cannot place the tappings on the low voltage winding because it is near to the core. You cannot place the tappings in near to the LV winding. Nah. So tappings can be easily provided and can be easily accessed on the high voltage winding. You place the tappings here because it is out of the core. Nah. So you can place the tapping. These are the tappings. The tappings can be easily placed on high voltage windings and can be easily accessed. If it is a high voltage winding, therefore we can have a voltage variation from 0 to 220 kilovolts. If you place the tappings on low voltage winding, you can have an access from 0 to 11 kilovolts only. Variation in voltage is very large in this case. If you place the tappings on low voltage winding, variation is very less. So you can have a control for a large range on the high voltage winding. Moreover, whenever you want to change, while you are changing the tapping positions, it is very easy to change because the current carrying capacity in high voltage winding is lesser. Okay, so handling low currents is easy. Handling low currents is easy. Since HV high voltage winding carries low current. High voltage winding carry low current and low voltage winding will carry high currents. If you place the tappings on low voltage winding, whenever you are changing the tappings, it will experience huge sparks also. You don't get sparks on the high voltage winding. When you are changing the tapping, you will not get sparks on the high voltage winding. Okay, so these are some advantages with the by keeping the low voltage winding near to the core. The first thing is thickness is less, and the second thing is tappings can be easily accessed from the high voltage side. Large voltage variation can be done, and handling small currents is easy. Okay, now here the question is about direction of currents in the windings. Okay, we are placing the windings on the core. Okay, if we are placing the windings on the core, if the windings on separate legs, how do they carry the currents? If the windings on same leg, how do they carry current? Let me show you here. I'll prove it later. Let me show you here. You see, the first case here, completely high voltage winding. You just assume completely low voltage winding. That means what? High voltage winding is on one leg, low voltage winding is on one leg. Now to satisfy the Lenz's law, if high voltage winding carries cross and dot, low voltage winding is also carrying cross and dot. You see, right side cross, here also right side cross, left side dot, here also left side dot. If the windings are placed on separate legs, then they will carry same direction of current to satisfy the Lenz's law. I will show you the Lenz's law also. I'll show you the Lenz law. Now here half HV is there, half LV is there. Half HV is there, half LV is there. You see, if LV is carrying cross and dot, HV is carrying opposite, dot and cross. If the windings are on the same leg, then they will carry opposite direction of current to satisfy the Lenz law. Okay. If the windings are separated, then they will carry same current direction. If the windings are on the same leg, then they will carry opposite direction of current. It is very, very important to obey the Lenz law. Okay. So that is what he has given in the statement. If the windings are placed on separate limbs without interleaving, they must carry the currents in the same direction to satisfy the transformer action. Now, if the windings are placed on same limb with interleaving, half LV, half HV, then they must carry opposite direction of currents to satisfy transformer action. Okay, let me show you here. Let me show you the diagram here. The diagram is missed here. Let me show you the diagram. Okay, please try to understand this. I have a transformer core like this, and I have, let me take up the high voltage winding. Okay, let me take up the high voltage winding, and let me take up the low voltage winding. Okay, this is my low voltage winding one side, and this is my low voltage winding the other side, and this is high voltage winding one side, and this is the high voltage winding the other side. Now I am assuming that the current, I have given the supply to the high voltage winding. If I give the supply to the high voltage winding, the current is entering into the high voltage winding. Supply I am giving. Okay, I am giving the supply like this. So I have given the supply. Now this supply is going to drive the current like this. So here the current is entering, let us assume. The current is going into the left side of the high voltage winding. And then current is coming out of the right side of the high voltage winding. So I have given a supply. This supply is driving the current into the high voltage winding, and current is coming out of the high voltage winding like this. Okay. So it's a circular conductor, not a straight conductor, because this is a leg. On this leg we place the winding like this. Okay. So current is going in and coming out, going in and coming out. This is also circular conductor. Okay. Now because of current carrying conductor, flux will be produced now. Because of current carrying conductor, flux will be produced. How? The direction of flux can be obtained by using right hand thumb rule. So current is going in. So you should indicate the current direction with the fingers, closed fingers, curled fingers. Current is going in and coming out, going in and coming out. So the flux will be downward direction. So the high voltage winding is going to create the flux in the downward direction. Okay. So here it will be like this. It will be like this. So let me show you the direction will be, the direction as like this. So this is my high voltage winding flux lines direction. This is my phi HV. Okay. Maybe phi HV can be, let me mention with the other color, yellow color. Okay. This is phi HV. Alright. Now, as the supply is time varying voltage, current is time varying, and hence the flux is also time varying. This time varying flux line is linking with the high voltage winding. This time varying flux is linking with the high voltage winding. Therefore, an EMF induces in the high voltage winding, no doubt. The same time varying flux line is also linking with the low voltage winding, and hence EMF will induce in the low voltage winding also. The EMF induces in the low voltage winding also. Yes or no? Now the EMFs always should oppose the very cause of its production to satisfy the Lenz law. Here EMF will be induced in the winding and opposes the source. This EHV opposes the source. Now ELV, how it can oppose? We don't have a closed path now. We don't have a closed path. So you have to create a closed path. Then only EMF can drive the current, can produce the flux, and can oppose the very cause of its production. The cause for the production of EMF is phi HV. High voltage winding flux line. Therefore, it wants to oppose high voltage winding flux line. To oppose high voltage winding flux line, low voltage winding has to create a counter flux now. How does it create? With the current flow. How the current flows? When you create a load. Let us create a load here. Let us create a load here. I am closing a load. I have a load here. Right. Now, so now we, in order to oppose the very cause of its production, EMF is because of phi HV. Phi HV is in the upward direction. So phi LV must be downward direction, like this. Phi LV must be downward direction. Okay, phi LV must be downward direction, like this. Oh my God. Okay, phi LV must be downward direction. I am using the same color, so don't take it in another way. You can use different colors if you want. So this is the phi LV direction. Okay, phi HV direction is this one. Phi HV direction is anti-clockwise and phi LV direction is clockwise. Quite opposite it has to be. Okay, if you are expecting the downward direction of flux lines, what must be the current direction? Okay, if you are expecting downward direction, then the current has to enter on the left side of the turns and has to leave from the right side of the turns. So here the current must be, cross mark and dot mark. Current should enter here and current should leave here. Okay, current should enter here and current should leave here. If it is leaving, coming out, entering, like this. Okay, so this is how the cross and dot polarity. You see, windings are placed on separate legs. If the windings are placed on separate legs, then they will carry same direction of current. You see, must carry same direction. When they are placed on separate legs, they must carry same direction of currents. If half LV here, half HV here, then they must carry opposite direction. Let me show that also. Okay, let me show that also. I'm not going to draw the supply and all those things. You just imagine here. I'm keeping high voltage winding with the yellow color. This is my high voltage winding and the conductor sides. Low voltage winding with the other part. Let me take up the pink one. This is my low voltage winding. Okay, and this is one part and this is one part. And now this time I am using what I can say the current directions with the white color. You say, I have assumed the current direction in the HV winding as cross and dot. Let us assume the current direction in the high voltage winding or low voltage winding. Anything is okay. I am assuming the current directions in high voltage winding as opposite to earlier. So let me assume it as dot and let me assume it as cross. That means what? Current is entering here and current is leaving here. Current is entering here and current is leaving here. Okay, therefore the produced flux is going to be upward. High voltage winding is going to create the flux in the upward direction. This is the high voltage winding flux lines direction. This is the high voltage winding flux direction. As the current is alternating, flux is alternating. As the flux is alternating, an EMF induces in the high voltage winding and an EMF also induces in the low voltage winding. Why the EMF is inducing? Because of high voltage winding flux lines. Okay, why the EMF is inducing? Because of high voltage winding flux lines. High voltage winding flux line is because of current. Current is because of supply. So EMF opposes the supply here, satisfies the Lenz's law. But this EMF cannot directly oppose the supply, na? Because we do not have any connection. Low voltage winding induced EMF cannot have a direct connection with the supply. Do we have any electrical connection? No, only magnetic connection is there. That's the reason why it is driving a current and producing a magnetic field and compensating or trying to oppose the high voltage winding flux. In the same way, here also, ELV cannot oppose the voltage source directly. Therefore, it has to produce a flux in opposite to high voltage winding flux. If the high voltage winding flux is upward, low voltage winding flux must be downward. Low voltage winding flux must be downward or opposite to high voltage winding flux line. Okay, let me take up phi LV. If you are expecting the flux lines in the downward direction, what must be the current direction? Apply right hand thumb rule. If you are expecting current in the downward direction here, the current has to enter on the left side and has to leave from the right side. Yes or no? Current should enter here and leave here. So it will be, I can say it will be a cross mark and this will be dot mark. You see current polarities. If it is dot, cross. Cross, dot, opposite. If the windings are placed on the same leg, High voltage winding, low voltage winding. I place the same, I place the both the windings on same leg. Therefore, they they are carrying opposite direction of current to satisfy the Lenz's law, to satisfy the transformer action. This is must. Otherwise, what happens? Imbalance force comes and the transformer is no more a stationary device. It will be like a moving device. Okay. All right. So that's about the currents and the current directions in the windings. Let us move on to the next part, that is operation of the transformer. Okay. So I'll tell you. Let me recall the things. So far we have discussed about core construction, core features, and the type of the magnetic path, shape of the magnetic path, and the factors like iron factor, utilization factor. Okay, this kind of things we have discussed, and then we have discussed about windings also, how to place the windings. Okay, right, interleaved winding or sandwiched winding. All right. Now, when you place separately, when you place the winding separately, what happens? When you place the windings on the same leg, what happens? We have seen so far about construction, core construction and winding construction. So far the construction related theory is completed, and now once we have designed the magnetic path and winding, then let us use them combinedly and let us see the operation. Okay, here we will be discussing about operation of transformer. Here we will be discussing about operation of transformer. Okay, operation of transformer. Okay, all right. Operation of transformer. He has given it as ideal transformer. Ideal means lossless transformer. That means efficiency is 100%. Efficiency is 100%. Lossless transformer or efficiency is 100%. How do you get zero losses? There are two major parts. One is magnetic path, another one is winding. So he is expecting, if you are expecting zero losses, means in the magnetic path no losses should be there, in the winding also no losses should be there. Winding losses should be completely zero, magnetic path loss also should be completely zero. That is what he has given. You see, magnetic path loss means iron losses in the transformer core is assumed to be zero. Winding losses should be zero means resistance of the winding should be completely zero. Okay, if you are expecting zero iron losses, zero resistance, then is it possible? Is it possible to design with the zero iron losses? Is it possible to design with the zero copper losses? Not at all possible. So ideal transformer is just an imaginary transformer. Ideal transformer is just an imaginary transformer, which is impossible, which is not possible or impossible in practice. Okay, which is not possible in practice. There are other things also, like leakage flux should be, leakage flux should be zero. It's not possible, na? Definitely some leakage will be there. Right. The other thing, magnetization curve of the transformer core is assumed to be linear. Okay. He is expecting linear means in another way iron losses, the hysteresis losses should be zero. Like this, we'll be having BH curve, na? BH curve, BH curve, BH curve. So B and H, or otherwise I, phi. So if you draw the graph, it will be like this. He is expecting linear curve like this. If he is expecting linear curve means the area under the curve as zero. That is not possible. That means our hysteresis loss is zero, which is not possible. Okay. And one more thing, core, the permeability of the transformer core should be infinite. If mu is infinite, okay, if mu is infinite means the flux lines will easily establish through the core. We doesn't require an external MMF. We doesn't require an external MMF. We doesn't require an external MMF. We doesn't require a magnetizing component of current at all. Okay. While to magnetize the domains, external magnetic field should be there, na? External magnetic field has to magnetize the domains. Okay. The external magnetic field will be created because of current through the conductor. Now the current value is very minimal, to say exactly zero. Higher permeability means no need of magnetizing component of current, which means magnetizing component of current is 0. Higher permeability means magnetizing component of current is 0. He is saying that magnetizing component of current is 0. No excitation is required. Okay, no magnetization force is required. Is it possible to establish? Is it possible to establish the flux lines without demanding any magnetizing component of current? In practice, it is not possible. Every material requires some amount of energy, right? Even if I want to run, I have to eat 2 idlis at least. Then only I can run. Na? You feed some input, then I can work. To the transformer core also, you need to feed some amount of input in the form of hysteresis energy and eddy current energy. Those are the energies for the transformer core. For us it is loss. For the core, the energies are what? The energies for the core is hysteresis energy and eddy current energy. For us it is a loss. Okay. Is it possible to, I will tell you to run 10 kilometers or 100 kilometers without eating. Will you run? It's not possible, na? So similarly here also, you need to supply at least minimum amount of energy to the parts of the transformer. Then only they are ready to work, they are ready to perform. So ideal transformer assumptions are just imaginary, not possible in practice, not possible in practical case. So in practical case, how it looks like? Definitely you cannot design the core with infinite permeability, but you can design the core with highest permeability. Okay, mu should be very high. Mu should be very high. Okay, now coming to the iron losses, you have to design the iron losses with minimal iron losses. Okay, with minimal iron losses. You cannot make them 0. Because you need to give some energy to them, to the parts, then only they will work. Okay, you cannot make the resistance as 0. So let us make the resistance of the winding as minimum. Okay, now similarly, you cannot make the leakage flux as 0. You can make the leakage flux as minimum. Magnetization curve is not linear. Definitely it will be non-linear, and the area should be, the BH curve is a thin BH curve. BH curve area is thin or small. Okay. If the area under the BH curve is small, means the energy demanded by the core for the reversal of polarities for the eddy current losses will be less. Especially for reversal of the magnetization, magnetic polarities, north pole, south pole, north pole. To reverse their polarity, it will consume some amount of energy. That energy we call it as hysteresis loss. We will discuss in the magnetization procedure. Okay. So here area under the BH curve is going to be very small. You have to design like this. He is expecting 0, na? Here the area under the BH curve is 0. Linear graph is expecting. So this is not possible. This is at least small area is okay, fine. We can design like that. At least you can design like that. So these are the practical transformer core features. These all are practical core transformer features. So these are practical. Okay. Practically mu can be very high, iron losses can be very low, winding resistance can be very low. We can design like that. Leakage flux also we can make it low. Magnetization curve we can make it very thin. Okay. So these are the practical transformer features. Okay. We cannot design ideal transformer. We can design transformer practically with that. Okay. So let me go ahead with the operation of transformer. Let me go ahead with the operation of the transformer. That means definitely core will be having some iron losses. Core will have some high permeability but not infinite permeability. Okay. If it is having high permeability, then it will draw at least a small amount of magnetizing component of current. It will draw at least some amount of excitation current is required. Now MMF is required to establish the flux lines. So magnetizing current it will draw to establish the flux lines. So we will see the transformer operation of transformer. We are taking it as practical transformer. Okay, practical transformer on no load. Let us see first no load case and then we will move on to load case. Okay, let us see first no load case. All right. So let me take up here a core. I am taking a core here, right, and I am going to place a windings. I am placing more number of turns here, N1, and on this side I am placing less number of turns. I am making it as N2. Okay, and here I am going to place the alternating voltage source V of t, and I am providing a switch here, and I am not placing any load here, so I am making it as open circuit, or otherwise you can also call it as no load. Open circuit or otherwise no load. Open circuit or otherwise no load. Okay, so open circuit condition or otherwise no load condition. Now what I am doing is I am closing the switch here. I am closing the switch here on this side, N1 coil side. Okay, the moment when I close the switch, this voltage source is going to drive the current. Okay, the first current which is going to enter into the transformer is magnetizing component of current. The first current which is going to enter into the transformer is I mu, magnetizing component of current. I am writing here magnetizing component. Okay, the purpose of magnetizing component of current is to establish the flux lines. Why? Core needs a flux lines. No, core will carry the flux lines now from one side to another side. The purpose of core is to carry the flux lines. Who will create the flux lines? Magnetizing component of current. So we know the current direction here. In each winding we know the current direction here. I am not keeping in each winding. Therefore, this direction of current will create the flux in the upward direction. Okay, so let me draw here the flux lines direction. Okay, let me draw the flux lines direction here. So this I am calling it as mutual flux. I am not indicating any leakage flux. You can assume some leakage flux also, but for timing I am not indicating any leakage flux. So magnetizing component of current is creating the mutual flux. Now whenever this flux is establishing, as a voltage is time varying, current is time varying. If current is time varying, flux is time varying. If flux is time varying, then EMF will be induced at the N1 coils, EMF will be induced at the N2 coils. Yes or no? EMF will be induced at N1 coils, EMF will be induced at N2 coils. Okay, so here EMF always opposes the supply voltage, because the induced EMF is because of phi m is because of I mu is because of supply voltage. We have a direct connection between E1 and V. Electrical connection is there. So if the polarities of voltage source here it is positive and negative, then the polarities of induced EMF here also it should be positive and negative. Then only it can oppose the voltage. Yes or no? If it is 100 volts, then it will be 100 volts. Now you see the potential difference, 100 minus 100, it is 0. Opposition is done. If the polarities are minus plus like this, plus 100 plus 100, it will be 200. If the polarities of induced EMFs are, if the polarity of induced EMF is quite opposite to supply voltage, that is not opposition. That is not opposition. Okay, the polarities of induced EMF should be same as the supply voltage to satisfy the Lenz's law. Okay, now as the EMF is opposing the source, I am writing E1 is equals to N1 into d phi by dt. You can call it as mutual flux also, no issues, d phi m by dt. Because E1 na, induced EMF on the N1 coil, so N1 into d phi m by dt. No need to write the negative sign here. Because EMF polarity is same as the supply voltage polarity, EMF is opposing the source, it is satisfying the Lenz law. EMF is satisfying the Lenz law. So no doubt here it is positive terminal and negative terminal. Generally the positive terminal is indicated with a dotted terminal. Okay, we will take up dot terminal as a positive terminal for the connection purpose, for our convenience purpose, because once the transformer is designed and send it to the market or send it to the utilization point, we don't know which terminal is positive, which terminal is negative. So they will put some dots. So by observing a dots, we should assume that they are positive terminals. Okay, that means like phase should be connected here, not neutral. You have to understand like that. Okay. Now similarly here E1 is opposing the source and is satisfying the Lenz law. But what about E2? E2 EMF is generating, but it cannot oppose the very cause of its production. The cause for the production of EMF is mutual flux. How it can oppose? Okay, it has to drive a current, it has to produce a flux. But to drive the current, we do not have a closed path. Therefore, here the current is 0. I2 on this side it is 0. Therefore, the flux on the secondary side is also 0. There is no counter flux for the mutual flux. Here, opposition is not happening. Lenz law is not happening. Lenz law is not satisfied from the secondary side, but it is satisfying from primary side. Alright. Now here, once the magnetization is done, and of course the EMFs are induced, parallelly actually, whenever the magnetization is happening, we'll be having some electrons, no, here and there. We'll be having some electrons here and there. Why? Because the core is not completely a magnetic material, perfectly not 100% magnetic material. It will possess some impurities, and due to that impurities some electrons will be existed. And whenever the magnetization is happening, whenever the magnetic flux lines are establishing, north pole, south pole is creating, then this electron may experience a force and it will tries to move from one place to another place. This electron will experience a force and tries to move from one place to another place. This will also experience, this will also experience, this will also experience, and this will also experience. We call these currents as eddy currents. We call these currents as eddy currents, and the losses are called as eddy current loss. Okay. And the losses are called as eddy current loss. So totally in the core, magnetization is happening and eddy current loss is also happening. Okay. Whenever the magnetization happens, that means what? Inside the core, dipole has to be magnetized. Now, all the poles has to be oriented in the same direction of external magnetic field. Okay. In order to, if all the poles has to magnetize in the same direction of external magnetic field, if I take up like this, okay, like this. Okay, this is the external magnetic field. Now here inside the dipole it will be like this, randomly it will establish. Now to change the direction in the same direction of external magnetic field, like this, all the dipoles should be oriented in the same direction of external magnetic field. To orient or to change the directions of dipole, it will consume some amount of energy. The energy consumed by the core, we call it as hysteresis energy or hysteresis loss. For us it is loss, for the core it is energy. Then only it can perform the work. Na? So here, while the magnetization is happening, this leads to hysteresis loss and this leads to eddy current loss. Inside the core, there are two loss components. One is hysteresis loss, another one is eddy current loss. And together, we call it as core losses. The core losses or total iron losses will be what? The total iron losses will be hysteresis loss plus eddy current losses. These are going to depend upon magnetization or magnetic flux density. Okay, of course, magnetic flux density and thickness of the core. If the thickness is more, volume is more, the core loss is also going to be more. We will have a formulas later. If you want me to write, I'll write here. The hysteresis loss is proportional to B maximum power X into frequency into volume of the core. V is nothing but volume, not voltage. F is the frequency, B is the flux density, and eddy current loss is proportional to B maximum square, F square, and thickness of laminations. thickness of laminations. We are using small thickness now. Because of small thickness, eddy current loss is going to be minimized. If you use small thickness of insulations, eddy current loss is going to be minimized. Okay. Now here hysteresis loss is happening, eddy current loss is happening. One current is creating the flux lines. Magnetizing component of current purpose is only to create the flux lines. Magnetizing component of current purpose is to create the flux lines. But this hysteresis loss component and eddy current loss components are going to be supplied by another current that is I can say working component of current, or we also call it as core loss component of current. Working component of current magnitude and core loss working component of current magnitude and magnetizing component of current magnitude, phasor sum of these two or vector sum of these two, we call it as no load current. We call it as no load current. You know why the currents drawn by the transformer is 2? Because the magnetic path has two natures. This magnetic path has magnetic properties. Okay, the magnetic path has magnetic properties and conducting properties also, na. Okay, magnetic property demands flux establishment. Conducting properties demands electron movement. Of course, the conducting property leads to electron flow. Magnetic property leads to flux establishment. Conducting property leads to, end of the day, heat dissipation. Okay, so magnetizing component of current creates the flux lines. Working component of current creates the hysteresis loss, or working component of current supplies the hysteresis loss and eddy current loss. For us it is a loss, but for the core it is a energy. The energy supplied by this working component of current, so that transformer core is now fully magnetized and it has consumed the energy whatever it wants, and then now it is ready to transfer the power from one side to another side. I want to transfer the power from this side to this side. If you want to transfer the power from this side to this side, the medium has to be energized first. Na? The medium has to be energized. Then only it can work. How I am energizing? By creating the flux lines and by supplying the energy which is demanded by the core. What is the energy which is demanded by the core? Hysteresis energy, eddy current energy. For us it is a loss. For the core it is an energy, minimum energy required. It is like a food for the core. Okay, right. So let me show you in phasor diagram. Let me show you in phasor diagram as well as the EMF equation also. It will be like this. Okay, if you go ahead with the phasor diagram, let me take up the phasor diagram like this. I am taking or else let me take up the EMF equation first, and then I will draw EMF phasor diagram later. So if you look at EMF equation, it will be like this. Just now we have seen E1 I have taken. The same thing will be happen for E2 also, because the same polarities has to be there, because EMF has to oppose a very Clausewitz production. So E, I am just roughly taking E is equals to N into d phi by dt. Okay, what is phi? Alternating flux. So let me take up it as phi m into sine omega t. If you take up differentiation of sine cos omega t into omega. Okay, now omega is an angular frequency. We can write it as 2 pi f. So I am writing this as 2 pi f. Okay, so this I am writing aside 2 pi f into f into pi into cos omega t. Okay, this cos omega t we can write in another manner also. Cos omega t I want to write in terms of sine. Sine and cos are differed by 90 degrees. So if you want to write cos in terms of sine omega t plus 90, sine omega t plus 90 or sine 90 plus omega t. Okay, sine omega t plus 90. So if you look at this one, EMF is a sine wave, flux is also sine wave, but there is a phase displacement of 90 degrees. There is a phase displacement of 90 degrees. Between the flux wave and induced EMF wave, there is a phase displacement of 90 degrees. If you represent the phase displacement, it will be easy for us. How can we represent? If the flux wave has reference, if the flux wave as reference, if I take the flux wave as reference here, then where should I represent the EMF wave? The EMF wave should lead the flux wave by 90 degrees. Na? Should lead the flux wave by 90 degrees. So the EMF wave will be here, like this, 90 degrees leading. Okay. In some of the textbooks, they used to represent with EMF in the downside. If you want to get the EMF on the downside, simply they will be taking the EMF as negative polarity. That's it. If they take negative polarity here, it will be negative. It will be negative. Here also negative. Negative sign. Okay. Instead of positive sign, it will be negative sign. So it will come on this side. EMF lags the flux by 90 degrees if you take EMF polarity as negative. I don't want to take EMF here negative n into minus n into d phi by dt, because polarity should be positive if EMF is satisfying the Lenz's law. If EMF doesn't satisfy the Lenz's law, then you can take up negative polarity. Okay, both, even you draw the phasor diagram downward by assuming negative sign also, fine, that is also correct. Okay, I will draw with that case also. Okay, fine. So this is how the displacement between EMF and flux exists. Now let me continue this EMF equation. If I continue the EMF equation, if I want to get the maximum point, if omega t is equals to 0, at omega t equal to 0, okay, if omega t equal to 0, then we will be having sin 90. Sin 90 is maximum. Sin 90 value is maximum. Then I can write E is equals to E maximum. What is that E maximum? 2 pi f n into phi. 2 pi f n into phi. Okay. But I want, in generally, the alternating currents are represented in terms of RMS values. Let us take up RMS values. The RMS value will be E maximum by root 2. So if you divide this E maximum value by root 2, then you will be getting it as 4.44 into f into n into phi m. So this is the RMS value of the RMS value of the induced EMF in the windings. Okay, if you use N1, it will be E1 RMS. If you use N2, it will be E2. Okay, let me show you here. E1 divided by N1 and E2 divided by N2. If I bring this N on the left side, so E1 by N1, E2 by N2 is equal to same remaining constant value, na? 4.44 into f into phi m. This is very, very important. What actually it is? EMF per turn on both the sides of the transformer is same. That is 4.44 into f into phi m. Okay, EMF per turn on both the sides of the transformer, is same. How much is that? 4.44 into f into phi m. Even you can write phi m also in terms of flux density and area of cross section. Net area of cross section also you can write. Okay, this point you just remember. We will take the use of this, and then later in the transformer operation, and then later let me continue that with the phasor diagram. Okay, let me continue with the phasor diagram. If I go with the phasor diagram can be drawn like this. Okay, first I wanted to show you here. I said the core has two properties. One is magnetic property, another one is conducting properties. The magnetic property I can represent with inductor, and the conducting property I can represent with resistor. Okay, right. So inductor is an element which converts the electrical energy into magnetic field. So who is creating the magnetic field here? Magnetizing component of current. So inside the inductor I can represent I mu. Here inside the resistor I can represent IW. Inside the inductor I can represent I mu. Okay. Now these are core natures I am writing. These are core natures. So therefore the phasor diagram will be like this. Phasor diagram will be like this. I have a supply voltage. Let me take up it as supply voltage. Now with respect to the supply voltage, the current lags. Which current lags? Inductive nature of current lags. Why inductive nature? Because the core has two properties. One is magnetic property, another one is conducting property. So the magnetic property I am showing here. I am showing here like this. This is the magnetizing component of current. This is the magnetizing component of current because of inductive nature or magnetic property, which the purpose of this current is to create the flux lines. The purpose of this current is to create the flux lines. Okay, so the flux lines will be in phase. The flux lines will be in phase. Let me represent with this as the flux and this as current. Because phi is directly proportional to I na. Phi proportional to I, so current is in phase with the flux is in phase with the current. And now what is other property? The other property is conducting property. So the conducting property we will be representing with resistance. In the resistance, the current is in phase with the voltage. This is working component of current. We can represent this is with the this is the working component of current. We represent it as R naught and we represent it as X naught. Some textbooks they represent with B naught, G naught and B naught. G is nothing but reciprocal of resistance. B is nothing but reciprocal of reactance. That's it. Nothing new. Okay. Now the phasor sum of working component of current, and magnetizing component of current is nothing but no load current I naught. It's nothing but no load current I naught. The angle between supply voltage and no load current. The angle between supply voltage and no load current. This is theta naught. Generally, theta naught is the no load power factor angle. No load power factor angle. Theta naught is around 80 degrees to 85 degrees. Therefore, cos theta naught will be very low, which will be around 0.2 lagging. Very low power factor. Very low power factor. That is the reason why you might have observed during open circuit test of the transformer or open circuit test of the induction motor, we will be using low power factor wattmeter. Why low power factor wattmeter? Because the theta naught is very large. Cos theta naught, cos of 80 degrees or cos of 85 degrees will be very low power factor. To sense that low power factor, we use low power factor wattmeter on open circuit test. Why low power factor? Because I mu is very larger than IW. Why is I mu is very large? Because the core possesses more magnetic property and less conducting property. Okay, because of more magnetic property, magnetizing current is more to set up the flux lines. Okay, because of less conducting property, the conducting current is less. This is going to create the heat here. This is going to create the heat dissipation. And R naught is going to represent the iron loss component. That is hysteresis loss plus eddy current loss. Okay, R naught is going to represent the iron loss component, not I mu. I mu is just to create the flux. That's it. For the reversal of flux lines, energy is required. Who is supplied? Hysteresis energy. Okay. For the eddy current energy, that is what? Who is going to supply? IW. Okay. Core loss component, working component, magnetizing component doesn't create any loss. Working component will create a loss. Okay. So the summation of these two is no load current. Generally, here I mu is around 4 to 5% of full load current and IW is 1 to 2% of full load current. 1 to 2% of full load current and I mu is 4 to 6% or 4 to 5% of full load current. Okay. Totally, no load current will be around 5 to 6% of full load current. 5 to 6% of full load current. You see, there are other things also. To be. This is I mu, and I can also take up this also I mu, right? If this is IW, this is also IW, right? This is also IW, right? Okay. Now theta, opposite side is I mu, adjacent side is IW. So you can represent sin theta, cos theta also. You can represent sin theta, cos theta also. So here sin theta naught is equals to sine theta naught is equals to opposite side by adjacent side, that is I mu divided by, hypotenuse. Hypotenuse is I naught. Okay, so magnetizing current is equals to I naught into sine theta naught. Magnetizing current component is a sine component. And if you see the working component of current, you can write here cos theta naught is equals to adjacent component, working component divided by hypotenuse, that is I naught. So working component of current is I naught into cos theta naught. Loss component is a cos component. Cos component of current creates a loss. Sine component of current creates a flux. Even you see the active power formula, V into I into cos phi, that's a heat dissipation. Okay, that's a heat dissipation. V into I into sine phi, that's a magnetic field creation or electromagnetic field creation, not energy loss. So this creates a reactive, this is a reactive nature. Okay, and this is a active nature, active component, lossy component, and this is a lossless component. Okay, lossless component. Okay, so these are some things to be understood from the phasor diagram, and I wanted to represent the other point, that is EMF. Where should I represent EMF now? I can represent the EMF leading with respect to flux. I can represent the EMF leading with respect to flux by 90 degrees like this. EMF almost equals to, this is even, because N1 is greater than N2, na? We have seen. I have taken so many turns, N1 is greater than N2. So this is high voltage winding and this is low voltage winding. So E1 is greater than E2 obviously. E1 is greater than E2 obviously. E1 is almost equals to V, supply voltage. Why? Supply voltage must be equals to induced EMF plus in between the drops. Na? So there should be a drop. EMF plus drop is equal to supply voltage. I am not representing the drops because the current is very small, just 5 to 6% of current. So I am not representing the winding resistance drop, leakage reactance drop at all. Okay, we will discuss those drops in the load, during the load, because during the load the current is more. If the current is more, drops also considerable. Here the drops are not considerable. So that's the reason why E1 and E2 I am drawing like this. Okay, E2 is less than E1 since N2 is less than, E2 is less than E1 since N2 is less than N1. Okay, now if you want to project the induced EMFs in the opposite direction, you can project, still you can project. Okay, right, let me show you that also. Supply voltage, magnetizing current, and it will create the flux. Magnetizing current purpose is to create the flux. Working component of current is going to create the loss, and the sum of these two is a no load current. The angle between no load current and voltage is theta naught. Okay. Now if I take up the induced EMF's polarity as this, if I take up the EMF polarity, if EMF polarity is opposite to supply polarity, then EMFs are taken as minus n into d phi by dt, that's it. If you take up minus n into d phi by dt and solve it, you will get minus sign. Okay, so you will be getting it as sin omega t minus 90. Sin omega t minus 90. So because of negative sign here, I am drawing E1 quite opposite to supply, E2 quite opposite to supply. So I can draw E1 approximately near to supply voltage, and E2 will be less than E1. Why E2 is less than E1? E2 is less than E1 since N2, number of turns on the second side, is less than first side. Okay, whatever the winding which is connected with the source, that is called as primary. Other winding is called as secondary or tertiary or anything. Why we are calling it as primary? Because that winding receives the power at the first instant. The winding which receives the power at the first instant is called as primary, and the next instance it will be received by the tertiary, secondary, tertiary, and so on. Okay, fine. So this is what about the phasor diagram of a transformer under no load condition. All the things are going to be same. I mu is sine component, IW is cos component or active component. So that is what we have seen here, the differences here. Let me show you the differences here. It's I mu, magnetizing component of current, IW, working component of current. I mu is not loss component, it's a reactive component. It won't create any loss. It creates a flux. It always in quadrature with the voltage, 90 degrees. Quadrature means 90 degrees. Its magnitude is around 4 to 5% of full load current. And working component of current is active component, cos component. Let me write here, I naught into cos theta naught. And this is I naught into sin theta naught. Okay, so this is what full and that is what less. Okay, it is always in phase, so it will be 0 degrees and its magnitude around 1 to 2% of the full load current. Okay, so there, like if you want to see, I mu is larger. Why larger? Because magnetic properties are more than the conducting properties. So I naught is approximately, the total resultant is I naught is approximately 5 to 6% of full load current. And if you see the representations of the two natures, the magnetic properties can be represented like this, X naught with an inductor. Okay, core can be, magnetic path core can be represented in terms of electrical parameter. R, L, C are the electrical elements, na? Okay, if any loss is there, we represent, if any heat is there, we represent with resistance. If the magnetic field is there, we represent with inductor. If electric field is there, we represent with capacitor. So here magnetic flux lines establishment, so we are representing with inductor. Here heat is there. Okay, inside the core hysteresis loss and eddy current loss taking place, heat dissipation is there, so we are representing with resistance. This is conducting property. Okay, so we represent with resistor because it is in phase with the voltage. We represent with inductor because it is quadrature. So that's what about the no load operation of the transformer. Okay, so we will see the load operation of the transformer possibly in the next session. Okay.